upper critical field and pairing symmetry into the Ising superconducting materials. So Lena, the stage is yours.
Perfect. Hey, thank you. So this will be a theoretical work that we will try to explain some experimental data. So it's a bit for everyone. So I'll be talking a bit about some work that Tristan introduced a bit yesterday for the first part. So we've been looking at some models to model basically the upper critical field in the plane for few layer TMDs. So when we still have mostly Zeeman coupling to spins, and when we don't have this orbital FFLO to really bother us. So this way. So we all know that the classical way to think about, if you have a superconductor, we have some superconducting condensate, maybe with singlet superconductivity, and if we then apply some field, and we know that it's a low temperature and it's a low field, it won't really give us enough energy to break up the superconducting pair unless we increase the field to some point, and then it suddenly breaks the pairs. And we know in regular BCS theory, we will call this limit the polyparamagnetic limit. And usually you do some experiment and see at what point you have phase transition out of superconductivity. You want to compare it to if it exceeds this limit. So the way that we'll, all right. And this case, we'll be talking about TMDs. We'll be talking 2 more TMDs than these, but as we have seen previously this morning, both for monolayer and for few layer TMDs, we have this really huge critical field that exceed this poly limit by quite a bit. And actually, we'll see if we get to that a bit at the end, but there are some explanations too why we go to higher fields, why we could have more layers, that it's suppressed and sort of stabilizes around some values, and it doesn't fluctuate when we have different immersion symmetry breaking. So we can look at that a bit more later. Yes, so we'll be doing a really simple model where we think of this from a thermodynamical perspective. So just that we have some superconducting state, we will be assuming some superconducting order, and we have some normal state. And then the critical field is just a field at which these energies are equal, and therefore you have a phase transition. Since we have experimental data close to the critical temperature, because it becomes huge low temperatures, we can do an expansion in small field, and instead of looking at the full thermodynamic potential, we only really care about the condensation energy at 0 field and the susceptibility difference between the normal state and the superconducting state. So this means that we can define the upper critical field as just the square root of this ratio. This means that this definition of this polyparamagnetic limit is done in a regular singlet superconductor. And we know that at 0 temperature, we have a simple form for what the condensation energy is, just a steady state, superconducting gap. We also have that the susceptibility difference. We know that at low temperatures, a small field won't do anything to the pair, because it's not enough to break it. So we know that also the susceptibility difference just depends on the density of states here. So that's how we get this value for the so-called poly limit, and it's just proportional to the size of the superconducting gap. Yes, but more generally, when we'll be thinking about other types of systems like TMDs, we know that this condensation energy remains roughly constant, but this susceptibility difference can vary quite a bit. So this is really the interesting quantity here. So to think a bit more about from band structure perspective, because we want to include some spin orbit coupling here, we know that if we have just some bands with some superconducting pairing that pairs from K to minus K, we know that if we apply some magnetic field, we know that what the normal state band wants to do is to polarize the bands, sort of split them according to the spin polarization. But if you have a singlet superconducting gap, as we said, obviously you can't split the bands so now that K and K prime have the same spin. So we know that the susceptibility in the normal state can be quite large, but in the superconducting state is basically 0. However, that's not a problem if you have a triplet superconductor, because then obviously it's not a problem splitting the bands in this way. So you know that the susceptibility difference between the different pairing symmetries is quite huge. However, if you now have spin orbit coupling, so you already have some spin split bands, and you now apply a magnetic field, it needs to be perpendicular to the spin orbit coupling, so in plane for a TND. We know that either if you have a singlet or a triplet, that you pair from K to minus K here. If you apply a magnetic field, since the bands are already split, the effect is that you start counting the spins in the bands. And this is not just an effect that happens at the Fermi surface, but it goes deeper into the bands. So this means that when you have a superconducting order parameter that gaps out the bands, you can still have a large susceptibility that comes from deeper within the bands. So the susceptibility difference is in fact quite small for both spin symmetries. We can think of this in terms of this susceptibility difference, where we know that then in orders of superconducting, we know that for spin singlet in the spin unit band, we get this Pauli limit because we have a large susceptibility difference. But as I said, for a triplet superconductor in a spin unit state, this difference is small, and we should get a large critical field that we divide here by a much smaller quantity. But the same thing happens for a singlet in a spin orbit coupled state. So here we should also have a large critical field. And this we can easily calculate analytically if you have some parabolic bands, and this is basically what we'll do in this work. So the question then is, if you have something that you measure in the superconductor, that you have a critical field larger than the Pauli limit, does that mean that you have an interesting pairing symmetry? The question is no, not really. As I said, both triplet pairing and spin orbit coupling will raise the critical field by quite a lot. But you can also have cases like here is twisted trilayer where we know that this Pauli limit is often given by a weak coupling connection from the critical temperature to the size of the gap. And that's no longer true if you have a strong coupling. So in a lot of these cases, you might just have, even though you exceed the Pauli limit by quite a bit, you might just have a singlet superconductor. So in our case, going to the systems that we're interested in, we'll be looking at 4 different TMDs. And we already got a nice introduction to these. We'll be looking at these 2H or 1H for the monolayer crystal structures, which means that we're interested in this inversion symmetry breaking around the transition metal, which gives us a large spin orbit coupling and a so-called Ising spin orbit coupling. And as we see in some other works, we have quite a lot of interesting phenomena in these different materials, but mainly we know that they're superconducting, and there's been quite a lot of different predictions for what kind of order you can have. We know that since we break inversion symmetry, we might have some mixed parity orders between singlet and triplet. But as Elke explained yesterday, if you have correlations, that might still mean that you can have a bunch of different orders. It's not set what kind of mixing you have. So we will be modeling this and thinking about it as 4 different materials that basically have the same type of band structure. So you can get a Fermi surface that looks like this. You have 3 types of pockets that you can have. And this Ising spin orbit coupling is a large spin orbit coupling out of plane that spin polarizes the bands either fully up or fully down. But an important thing that we really need to stress is that an important part of spin orbit coupling is that by symmetry, you need to have that it's odd in momentum. So it needs to be, if it's positive at K prime here, it needs to be negative at K. But that also means that if it respects crystal symmetry, it needs to change sign between K and K prime, which means that you have these noble lines where the spin orbit coupling has to go to 0. So for the different materials we're looking at, we'll be just looking at different magnitude of the spin orbit coupling, and then different doping so that we could have this gamma pocket or not. That's the only thing we're changing in the model for different materials. So getting to the data and what we actually want to have a better model of is that here I'm showing 4 different TMDs in monolayer, where here these dots are experimental data from different figures. So here I'm also showing the ratio of the spin-orbit coupling at the K pocket and the size of the superconducting gap, assuming that it's uniform from TC. So these are just values taken from experiment. So then if you use the more standard model, where you just calculate that you have these spin split pockets, like I showed earlier, it looks really nice for 2 of these. For the other ones, it looks really bad. It's huge compared to the actual data you have. Something has to be suppressing the critical field by quite a bit. And in this De La Barrera paper, they compare that, because here, like in this plot, compare for a fixed temperature and compare here this ratio. You see that these niobium and the tungsten compounds are quite close in magnitude. So if it was something like this order that would give us this difference, it would have to be like 3 orders of magnitude larger for the niobium diselenide. That's just not what they see in experiment. So we'll be instead explaining what's going on here due to this other observation that these 2 materials seem to be on a line where it's a linear dependence on this quantity. Well, these here depend on the square root of the quantity. And the simple observation is that these have this gamma pocket, these do not. And it turns out that that's super important for the critical field. And the very short explanation to get some idea of why that is happening is to think about this susceptibility difference. And we know that at this gamma pocket, we have this nodal line that have to intersect with the gamma pocket by symmetry. Know that at these exact points, the spin-orbit coupling goes to 0. At those points, if you had a singlet superconductor, it's just a conventional BCS superconductor at those points. While it's spin-orbit coupled superconductor at the others, we know that the susceptibility difference will be much larger than all the other ones. So what we will do is, even though we expect that there might be some mixed parity, we will just think about this in the simplest possible model, which is to just assume that we have a uniform spin singlet, and then compare to what we had before, what I showed with these plots, and then a model where we assume that we can have 3 pockets, so a gamma pocket and this KK prime pockets. And then we can, if we have a simple model, we can just calculate what the susceptibility difference is, and then the critical field. And then we can compare to if you had instead fully spin triplet pairing, what we get. I have some data for mixed parity, but I think we'll leave that to further discussions. Okay, so just a very quick summary to what we have in the model. As I said, it's just parabolic bands. The way we will modeling this is as if we had just 1 order parameter to the same temperature dependence on both pockets. So then you can just add up the susceptibility difference for the different pockets. And the only difference between them is that the spin-orbit coupling looks different. Otherwise, they're identical. So then the full critical field will just depend on this full condensation energy and full susceptibility difference. And just to give some insight to how you calculate the susceptibility difference, all you need to know are the bands in both the superconducting and in the normal state. And then it's just an analytical calculation. So to just show you the results, we calculate for the gamma and the K pocket separately, as I said. So for the K pockets, since the spin-orbit coupling constant and the superconducting gap is constant, we can see that it depends on this ratio squared, and it will be constant at all points. In this plot, I'm showing that for each K point, we can show what the susceptibility difference looks like. All K points, or K pockets, it's constant. However, if you now move to the gamma pockets, that's more interesting, is that if at each point we should have a ratio that looks like this. Obviously, when the spin-orbit coupling goes to 0, this should be the value that you have in a conventional superconductor. So what you actually get is this nice Lorentzian shape. You can fit the data and see that it's the nice Lorentzian, so you can just calculate when you integrate over this pocket. We see that instead of this squared ratio, we get a linear ratio here instead. And if you look at just where the contribution is coming from, it's mainly from these nodal points, but also if you increase the spin-orbit coupling, it becomes even sharper that it's really these points that matter the most. To give some idea of the assumptions that we're using here, because we're sort of just saying that we can add up the contribution from these different pockets when it's obviously like a multi-pocket system. What we can compare is to the experimental data that we have. We have two very important assumptions. They basically add up to that the order parameter acts as if it was just a one-band model. That basically means that at zero temperature, you have the same field, you have the same temperature dependence on the field, on the pocket, on the gap on both pockets. But we also know that for the critical field, it very much has this temperature-dependent shape, like in this example system, where you have this kind of square root temperature dependence that you only get for one pocket, and it does not have this kind of two-gap behavior when you should have this upturning temperature. So just using those assumptions and doing a very simple like mean field model, we can see that if we assume that this has to be the case, and then we say that also the pockets have to have a very different critical field if we would consider them separately, you can see that the only solution to actually give us this kind of system is that the interpocket and the intrapocket interactions needs to be very, very similar in size. So basically these very different responses from two different pockets act as one order parameter because they're so strongly coupled. So this is basically what we're doing when we're considering this susceptibility difference, that we can add them up for all pockets. It's the same assumptions. So to show you the data for this three-pocket model, we just plug in what we need to know is this ratios. When I'm for the selenide, this is basically 100. This is 1 over 100 squared, and this is 1 over 100. This is basically negligible. Like we don't really care about this part. So if you add up the susceptibility difference here, we can see that the only part that really contributes is the part from the gamma pocket. And we can compare here with the experimental data, where this was the previous plot that we had, and here is for the three-pocket model, where here I just varied with 20% the spin-orbit coupling to see that you could still have a bit of a change and still be very close to these values. And what we can see from this nice analytical expression is then if you only had the K pockets, we get something that is linear in this ratio that we were discussing before. And here we actually show that if it mostly depends on the gamma pocket, we get this square root ratio that we see in experiment. Here. Yes, just to quickly show, compared to then a triplet order parameter. Here we get back to that these nodal points are important if you have a singlet order parameter. If you have a triplet order parameter, the susceptibility difference when you have zero spin-orbit coupling is still very small. So basically, if you plot here the susceptibility difference for assuming it's a singlet and assuming a triplet, you see that at the K points, you have a very small difference. But at the gamma point, it's a huge difference, really. So if you have a model where you only have the K points, it will be really hard to distinguish these two. But if the gamma pocket matters, then you should have a huge signature difference between the different order parameters. Yes, I think this is just summarizing this, saying that basically if you have a singlet at the gamma pocket, this really can explain the experimental data. But if you have a fully triplet, that really should give you a value that is quite far off. And we can see that by now combining these different plots in the same one, we can now see that this plot that I was showing before is not like a fit between these points, but it's actually using these two models and just plotting the values for this different spin-orbit coupling ratio. So we see that if you have something that is predominantly singlet, it explains the data very nicely. We think this is actually a quite strong statement on what kind of order parameter you might have in this monolary case at least. And from these analytical formulas, you can also see that this scaling with spin-orbit coupling that we were talking about is actually quite unique in the case we have this nodal spin-orbit coupling because then you can have this scaling. So the question is then, we'll see how much time I have to talk a bit about multi-layers as well. We want to think about, can we use this square root scaling? So instead of just looking at the magnitude of the critical field, can you look at how it scales with spin-orbit coupling? And obviously that's a problem because you only have one spin-orbit coupling in a given material. But if you could have things like, for example, what we have for the monolayer here. For example, if you can dope the system. So here we just use the dependence on TC from this bilayer paper where they do liquid gate doping, I think, if I remember correctly. But the idea here is that if you can dope the system, for example, electron dope it here, you know from the symmetry of this Ising spin-orbit coupling that here at gamma point k equals 0, so an odd function has to go to 0, while at the k point the spin-orbit coupling is its maximal value. So if you electron dope, you should you decrease the effective spin-orbit coupling they have close to the Fermi surface. But if you only have k points, you should increase it. So if you have a singlet order parameter, you should have some kind of scaling that you can calculate depending on what kind of order parameter you have. And if you have a triplet, it should not really be affected by the spin-orbit coupling of the same. But this is a bit harder to achieve experimentally. So we can think a bit about other options that we have if you go to multi-layer cases. We'll mainly be thinking about the bilayer here, but we have some data to 5 layers. We will be thinking about the bilayer as being 2 copies of this model. But since the inversion symmetry breaking alternates between layers, you basically switch the sign of the spin-orbit coupling when you go to the second layer. And then you have some hopping that couples pocket by pocket. So what you should get is something that now is spin degenerate, and you see that these nodes sort of gap out a bit. But what we still have is that we believe that the superconductivity still is mainly intralayer, and the magnetic field is in couples in plane, or it couples on site. So it should couple to an order parameter that it's still within one layer, and which now only has some hopping to another layer, which sort of breaks this spin-orbit coupling and suppresses it a bit. In fact, what we want to look about a bit more is if we have some additional inversion symmetry breaking, so the model gets easier then. So you, for example, have some effect from the substrate that gives you an interlayer potential difference, or if you can have some displacement field that you can vary. What happens then is that you get this additional term, this delta mu, that can populate one layer more than the other. So you actually split the bands now and you recover these nodes. And since we know that the susceptibility difference, if we were to have mainly a singlet, comes from these points, you can write down an effective model for the susceptibility difference that we get exactly at those points or close to them. So what we can write down is an effective spin-orbit coupling per layer that now depends on this displacement field. And we can show that you should get the square root dependence on this now effective spin-orbit coupling. So you can vary this displacement field, you could get the scaling behavior. And here is just some of the data for the bilayer, just to compare what's happening here. That these black lines are the monolayer and our model. These teal dots are the experimental data for the bilayers. It's nibodium. And actually, this lower line is when you don't have a displacement field. So we expect that it actually suppresses the pretty more than we see in experiment. We're not entirely sure why. It might be because there's more parameters here that we need to take and have a show, and we can't really get them from experiment. But if we add some displacement field, we can match this, but it might be quite large to be induced by a substrate. And this suppression basically comes from that you have this hopping between layers, which suppresses the spin-orbit coupling. And to just show the last plot here is that then our idea is if you then can have a displacement field that you can vary, so you vary this delta mu, you can get for this free pocket model this nice scaling behavior. So if you can get this to be around a milli electron volt, you could vary and see that you're showing a log plot, that you can get this square root behavior if you can get something that is in the same range as the interlayer hopping. So I think I'll end there with just a summary. It's really this gamma pocket that we're really interested in to describe these models. And that it really is a large signature difference between a single and a triplet when we include it in the model. And that possibly we can think about these ways to do the scaling, since we now actually have some more control over what critical fields do. Yeah, so thank you.
Lena, we have some time for quite a few questions.
So the scattering times, if I understand correctly, you're assuming that the gamma gamma, kk prime, and gamma k scatterings are all the same, all reflected.
Yes, yeah, if I remember correctly, that's it.
I'm not sure that is correct according to the.
No, so it might not be that it's exactly the same.
Very
No, exactly. So the question is how much that matters. But yeah,
Because I mean we had numbers and
yeah, that's nice.
So I have a question. Based on your calculations, can you make a prediction which of the four materials of tantalum, sulfate selenide, diamond sulfate selenide would be the most stable towards in-plane magnetic?
Oh, I don't remember what the numbers are now, but it should be the one with the largest ratio. I mean, we still have
this ratio of the delta
yeah,
to delta to lambda.
Yes, exactly. Yeah. So, but yeah, there's more problems obviously with that is molybdenum and tungsten monolayers only are superconducting when you gate them. Obviously, they can get this data, but obviously,
So I think the experimental community, I think what we care about is the four of the niobium, tantalum, selenium, and sulfur. So these are the four materials that are accessible for fabrication. And in all cases, the monolayer should have a TC of about 3.
Yes.
It was never measured for tantalum selenide, but there's reasons to believe it should be around 3. And therefore, it would be good if we can get guidance from you of where we should be looking for the highest stability of the in-plane field.
Yes, because both of these should have, as you say, basically the same TC. So then it's the value of the spin orbit matters more, and then tantalum would be the one that has more than twice the ratio.
Why is it so much bigger? It's because of the atomic tantalum.
Yeah, if I remember correctly, they have slightly different orbital contribution at the different pockets. So yeah, I think it's more in plane in tantalum than it is delta plane orbitals.
So that's kind of something that. Okay, any other questions? Okay, so let's.